motion seems to be all around us, especially in our modern frenetic world. What this lecture is going to talk about is how do we conceive of and study motion? How did the medievals conceive of and study motion? We're going to look, in fact, at three subsets of motion. First, we'll look at the celestial spheres. How are they made and how do they move? Then we'll come down to Earth and look at motion in general, how medievals started to conceptualize the problems of motion, the foundations of the modern science of kinematics. And finally, we'll combine the two and look at medieval arguments over whether or not the Earth itself is in motion. Well, let's start with the celestial spheres and the question of astronomy in medieval Europe. European astronomy was significantly changed, like everything else, by the influx of Arabic and Greek works. The system of medieval astronomy was basically Ptolemaic and Aristotelian, those two. The first popularizing text, by popularizing I mean a text that isn't extremely mathematically technical, so the first popularizing text in medieval astronomy was one written by Al-Farghani in the 9th century, translated by John of Seville, one of those early Mozarab translators, translated in 1137. It gave the basics of the Ptolemaic system. This long remained a standard text, but it was replaced and improved upon by another work called simply The Sphere, in reference to the spherical cosmos, by Sacrobosco. Sacrobosco is his Latinized name. The author's original English name, because an Englishman he was, is John of Holywood. He taught at Paris, the University of Paris, from 1230 to 1255, and he wrote The Sphere while he was there in about 1250. Now, this work stayed a standard textbook on Ptolemaic astronomy, on astronomy in general, down until the 17th century. After the inventing of the printing press, it went through numerous editions. Well, one of the things that the Middle Ages inherited along with the Arabic works was a tradition of a tension between Ptolemaic views of cosmology and Aristotelian physics. What was the basis of this tension? Well, for Aristotle, he's really interested in the causes of motion and the way the universe functions in a physical way. That is, the Earth has to be at the center because that's the low point, that's the place to which heavy bodies naturally tend. Ptolemy, on the other hand, is interested in getting the positions of the planets right, having a predictive model, having a mathematical model that allows you to predict where planets will be and account for the observed phenomena in the heavens. The conflict comes in because in order to do this, Ptolemy moved the Earth from the center of most of the celestial spheres. The spheres orbit a point, an eccentric, which is not coincident with the center of the Earth. So this causes problems with Aristotelian physics. There's a tension there. Well, there was a strong tradition of anti-Ptolemaic feeling in Spain by a number of Arabic authors. Ibn Bajjah, known in the West as Avimpache, Ibn Rushd, known as Averroes, was probably the strongest proponent of this. He just wanted to get rid of Ptolemy entirely and go back to an Aristotelian system, regardless of what it did to the predictive elements of positional astronomy. Well, these Spanish controversies didn't actually produce any workable solution, unfortunately. But there was a solution that had been proposed earlier by Ibn al-Haytham, that is Al-Hazan, as he's known in the West. This was to combine the two systems. In other words, make Aristotle's spheres so thick that the deferent and epicycle could run through them like through a channel. This meant that the outside, the convex surface of each celestial sphere and the interior concave surface of each celestial sphere would actually be centered on the Earth. But then the orbit of the planet would run eccentrically through that thick sphere. So it saved both of the systems. This was picked up in Europe. First, we think, by Roger Bacon. Roger Bacon certainly praises this system, and several other Franciscans do as well. And it became a standard model for thinking about the universe. Once we have these thick spheres now, I should mention, we can have attempts to measure the distances to the planets, the thicknesses of those spheres. In other words, if the spheres are nested together with no space in between them, then we can use the thickness of the spheres to calculate the sizes of some of the orbits. Well, attempts like this were in fact made, the most famous by Campanus of Novara, an Italian, although he lived it's seemingly all over Europe. He was in Arles in the south of France, in Toledo in Spain, in England for a while. In the 1260s, he wrote a work called The Theory of the Planets, in which he attempted to give measurements for the size of the universe. He started with diameters of heavenly bodies. He says the sun is the largest. It has a radius of about 17,850 miles. Much too small for our modern calculations, but nonetheless of interest that he was trying to do this. The moon, much, much smaller than the sun, has a radius of just a little bit under 1,000 miles, so much smaller than we think now. He also tried to do the distances. For the moon, he says that the inner surface of the moon's sphere is 107,000 miles away. The outer surface is 209,198 miles away. Well, he's in the ballpark with that one. The moon's about 250,000 miles away on average, so Campanus is relatively close. The further he goes, though, the further off from modern calculations we get. Of course, it was very difficult for him to make these kind of calculations with the data and the instruments he had in the 13th century. For example, he says that Saturn's furthest distance from us is, very exactly, 73,387,747 miles away. This turns out to be 1/25th of the actual distance that we now know, but nonetheless it was an attempt to get a sense of the size of how big the world was. And for a medieval, 73 million miles is pretty big. It must have been overwhelming to think of the universe as being that large. Well, once we have celestial spheres, and celestial spheres that carried the planets were accepted as real, as solid objects, real objects, by essentially everybody in the Middle Ages. The question is, what makes them move? Well, here there's a problem. You know that the traditions of Aristotle were very important for the Middle Ages. Aristotle was ambiguous on this point. Actually, that's being too generous to Aristotle. Aristotle was self-contradictory on this point because he says two very different things. In his work On the Heavens, De Caelo in Latin, as it was known in the Middle Ages, he says that the heavenly spheres are made of the quintessence, and quintessence has a natural motion circularly, just the way a rock naturally falls straight down to the center of the earth because it's made of earth. So too, the celestial spheres naturally turn in uniform circular motion. But in the physics and the metaphysics, he talks of what he calls unmoved movers, which are some kind of intelligences that are external to the orbs, but cause them to move without being affected by them. In some places, it seems that he even says that the spheres are ensouled, that they're alive or intelligent and move themselves. Well, getting back to these unmoved movers, how do they move the spheres? Again, Aristotle doesn't give us much help. He says they cause the motion by being loved. Now, what on earth does he mean by that? Well, we can say, yes, well, love really does make the world go round, doesn't it? Well, perhaps that sentiment itself, which was expressed in the Middle Ages, in fact, it's expressed by Dante for one, may in fact have its original source in this cryptic comment by Aristotle. But medievals didn't think very much of that explanation, nor could they quite figure out what it meant in all cases. So they tried to find other solutions. Naturally, in a Christian context, God can be seen as the single unmoved mover. So God causes the motion. But that tends to violate the theological principle that God works through secondary causes. And so some people instead proposed the idea that there were angels, which are creation of God, causing the spheres to move. So at least that's a secondary causation. But, that didn't satisfy some people either, because it tends to violate the principle of naturalism that was so important in many contexts, that there have to be natural causes to things. We don't want to have recourse to supernatural causes unless we can't avoid it. So some others, like the 13th century Englishman Robert Kilwardby, said that at creation God had implanted a natural motion in the spheres. This is very similar to what Aristotle says in On the Heavens. Others argued that God had merely given a sort of a push to the spheres to get them going, and then they would keep moving then forever after. One of these characters was Jean Buridan, a master at Paris, lived from about 1300 to about 1358. One of the few philosophers we've seen in this course who was actually not a theologian. All of his writings deal with natural phenomena, particularly with Aristotle. He invents the idea of impetus, as he calls it. It's somewhat akin to our notion of momentum. It's not exactly the same thing, but it's akin. It's an impressed force that keeps a moving body moving. And it was used, among other things, to explain projectile motion. Well, the heavenly spheres, since there's no resistance, they're not moving through a medium like a projectile through the air, the impetus shouldn't be dissipated. In other words, they shouldn't slow down once they're started. Well, a person who's often mentioned in the same breath with Jean Buridan is Nicole Orem, a younger contemporary, also a master at the University of Paris. He eventually became Bishop of Lisieux. He was born in Normandy around 1325 and died in 1382. He wrote something very interesting. He said that the celestial spheres were constructed in such a way that they're like a clock. And the way a man builds a clock, winds it up, and then the motion continues in the clock thereafter under its own power, so too God could have created the world in such a way, gotten it started like the clock, and it just keeps perpetuating its own motion, and unlike a clock, doesn't run down. So as you can see, there was a considerable diversity of opinion on the subject of what keeps the celestial orbs moving. Well, after looking at the heavens, let's look at motion in particular, that is, motion in general, specifically the dynamics of moving bodies. Now, some very important developments occurred in this field in the 14th century. And interestingly, what I want to emphasize here is that this very scientific topic, the kinematics of motion, actually seems to have developed out of a purely theological speculation made a couple of centuries earlier. So let's start instead in the middle of the 12th century with the theologian Peter Lombard. Now, I've mentioned Lombard to you before. He wrote those 4 books of sentences, or 4 books of opinions, which are interpretations of biblical passages, interpretations of Christian doctrine. He asked a question. It's in the first book, it's distinction number 17, about how grace or charity could be increased in a person. Can a person become more filled with grace or more charitable? If so, how does this happen? Well, he answers that since grace and charity are gifts of the Holy Spirit, they are absolute quantities. That is, so an apparent increase in charity, if a person becomes more charitable, more filled with charity, it's only because of his increased participation in absolute charity. There's actually not more charity in him. Well, as you know, all of the theologians who wanted to get degrees in theology had to write a commentary on Peter Lombard's books of sentences. And that meant writing a commentary on Book 1, Distinction 17. One of the commentaries proposes an alternate answer that disagrees with Peter Lombard's original conclusion. This was proposed by the Franciscan theologian John Dunes Scotus, or John the Scot. By the way, I should mention that in the Middle Ages, Scotus, the Scot, doesn't mean what we call Scots. It means Irishmen. The Scots were then called the Picts. He was born about 1265, died in 1308. He argued that charity could be added incrementally. And in fact, every quality in a person or in a thing could be added incrementally, and so was augmentable or diminishable. This notion came to be called the notion of the intention and remission of qualities, the increase and decrease of qualities. Now, shortly thereafter, after John Dunes Scotus, sometimes called the subtle doctor, after he proposed this, the notion was applied not only to Aristotelian motions of quality, but motions of place. Now remember, think back to Aristotle. Aristotle says there are three kinds of motion, three kinds of change. Motion of place, from point A to point B, what we think of as motion. Motion of quantity, when magnitudes change, that is, when the quantity of something changes. And motions of quality, as for example, when a green apple turns red. There's a change in a quality from greenness to redness, from sourness to sweetness. Well, once this notion was applied not only to motions of quality, like less charitable, it could also be applied to motions of place, that is, an object moving from A to B, or moving with increasing speed. So speed is a quality, so we can add speed. Well, what happens, importantly, is that around 1330, a group of people called the Oxford Calculators began to use the intention and remission of qualities to talk about local motion. These characters, three of them are William Heytesbury, John Dumbleton, and the rather unfortunately named Richard Swineshead. They were all scholars at Merton College, Oxford. They defined for the first time notions of uniform velocity, uniform acceleration, and they tried to get a handle on the notion of instantaneous velocity, that is, velocity at one given instant during an acceleration. They defined uniform velocity as the traversal of equal distances in equal intervals of time. Okay? And that uniform acceleration was the addition of equal increments of velocity added in equal intervals of time. So that's essentially the modern definition, expressed in a slightly different way, though. They also devised something called the mean speed theorem. Now, this is a little bit difficult to conceive of, especially the way they express it, because they didn't have mathematical formulas the way we do. The mean speed theorem goes something like this. Assuming that there's uniformly accelerated motion, a body going from 0 to 60 miles an hour or something, and it's accelerating uniformly, a body will travel the same distance in the same time as another body moving at a constant velocity, which is the mean between the starting velocity and the final velocity of the first object. Okay? So in other words, if we have an object that's starting at a speed of 0 and it goes to a speed of 8, it will traverse in a given interval of time the same space as a body moving with a velocity, the mean between 0 and 8, in other words, 4. Well, why is this important? Well, first of all, it sets the foundations for kinematic motion. The truth of the mean speed theorem was proven geometrically by Nicole Orem around 1350, and Orem's proof was very well known thereafter. But there's something important here. because Orem's geometrical proof of this mean speed theorem shows up once again about, well, not quite 300 years later. It shows up in 1638 as the fundamental axiom of the new science of motion in Galileo's Two New Sciences. So here, Galileo, an accepted, a recognized founder of modern classical physics, of the kinematics of motion, is dependent upon these medieval Oxford calculators, who in turn were dependent upon the results of a rather obscure theological question first propounded in the middle of the 12th century. So this example shows us how enormously far a succession of ideas can move from its original source. A 12th century theological query about the Holy Spirit, about grace and charity, eventually contributes to a fundamental axiom of kinematics. I don't need to argue much more now about how wide a view we need to take in doing the history of science. We can't isolate out things that we recognize as scientific, because whenever we do that, we miss the context and the causations behind things. We miss a lot of the influences that come in, originate from what we would recognize as non-scientific endeavors. Well, finally, let me now move to the last topic for this lecture, that is the motion of the Earth itself. We have no evidence really of anyone trying to say in the Middle Ages that the Earth moved around the sun, that it had an annual motion. But we do find people talking about diurnal motion of the Earth, that is, rotation on its axis. The first indication of this is a curious comment by William of Conches. Remember, he's the Chartrian master in the first half, middle of the 12th century, who's so interested in natural philosophy. In his dialogue, the Dragmaticon Philosophiae, which is between William as the philosopher and a duke, the Duke of Normandy, at some point the Duke asks him, well, what do you think about this business about the Earth being in motion? And William replies, saying, oh, you must be under the influence of that crazed philosopher who's always in a frenzy before lunch and drunk after lunch. The implication being that since he's drunk all the time, he feels the Earth moving under his feet, because that's the only reason anyone could come to such a crazy notion. Well, the Duke says, come on, you've got to give me a better reason than that for the stability of the Earth. Don't just tell me that he's drunk. And William says that, well, Earth is made of earth, and Earth is not a mobile element like fire. So it doesn't make sense to have Earth actually in motion. And commonsensically, who would ever think that the Earth is actually moving? We don't feel it move at all. The curious thing, the mystery here is, about whom were they talking? We have no idea. All we can say is that somebody was raising this question in the 12th century, maybe more than one somebody. We don't know who they were or where they were. Well, the topic comes up again in the 14th century under the guidance of Jean Buridan and Nicole Orem. Buridan noted that as observers, we can only ever observe relative motions. We can't really know absolute motions. So if we're in a boat going along the coastline, we really don't know whether the boat we're in is moving or the coastline is moving alongside us. We really can't tell. Nonetheless, Buridan rejected the idea that the Earth was rotating based on the fact that if you shoot an arrow straight up into the air, it falls back to the ground exactly where you shot it from. If the Earth were rotating, the arrow should be left behind. The Earth, in other words, would rotate under it, and so it would never return to its starting point. Now, his younger contemporary, Nicole Orem, later argued that the arrow experiment doesn't prove anything. The arrow also has an impressed horizontal force that it picks up when it's shot from the Earth that keeps it moving along with the Earth. Moreover, Orem uses a very interesting argument based upon what things look like on a moving ship. Very similar, in fact, to the same kind of arguments Galileo would use 250 years later. He says that if we're on a moving ship and we put our hand on the mast and move our hand up the mast and then down the mast, for any observer that's on the ship, the hand looks like it's moving straight up and straight down. But to an observer who's not on the ship, it looks like there's also a horizontal motion. The hand is not moving straight up because what they would see is the combination of the motion of the ship sailing along and the motion of the hand. And so we would see two different things from two different vantage points. Moreover, he says, all the motions that we can do on a moving ship look the same to the sailors on the ship, whether the ship is moored at the dock or is sailing very fast on the ocean. What he's getting into here is an idea of frames of reference. He didn't call it that, but it's an idea about frames of reference, which is, of course, very important in the physics of motion. He also notes that it's much more economical if the Earth turns once in 24 hours, rather than having every single celestial orb do that motion itself. It's more economical just to have the little Earth do that than the great celestial sphere, which seems to move all the planets, the sun and the moon, and all the stars around us in 24 hours. However, in the end, after a long logical disputation, Orem actually rejects the possibility of a moving Earth. Before doing this, however, he concludes that there is simply no way to decide the issue. Logic and reason cannot possibly give us the answer as to whether it's us moving or the stars, the sun, and the planets moving. We just can't tell. Reason fails us, so he falls back onto what is the more commonsensical answer. The Earth doesn't seem to be moving. It doesn't make sense for it to be moving. No one has ever proven it's moving. There are no observations that tell us it's moving, so we'll just stick with the traditional view that it is stable. Question is, why does he do this? Well, it's not just about the motion of the Earth. It's about, in a larger sense, the use of reason to answer very difficult questions. He says, and I'll quote from him, "What I have said here, by way of diversion or intellectual exercise, can, in this manner, serve as a valuable means of refuting or checking those who would like to impugn our faith by argument." What does he mean by that? Well, he means that reason is a very powerful thing, but there are limits to what reason can actually show us. Like, it can't tell us about the motions of the Earth, whether it moves or not. It can't answer that question. Similarly, if it can't answer a physical question about the world like that, we have to be very careful about the use of reason in discussing theological articles of faith. That is, faith should not be impugned too easily by reason. What Orem has done is actually very clever. He's used rational argument to show the potential insufficiency of rational argument, which is an amusing self-reflexive action. Well, in sum, we can see how the physics of motion and the physics of the heavens and the earth were important topics for medieval speculation. Many different views were proposed about the motion of the heavenly bodies, arguments for and against the rotation of the earth, and the formulation of basic theorems of kinematics. Well, we've spent a long time now in the medieval period, and the time has come for us to take our leave of it. In the next lecture, we're going to look at changes to European thought which took place in the late Middle Ages. That is, we are ready for the transition from the Middle Ages to the Renaissance. But how much of a transition was it?